can start the second lecture of today. We have Alberto Cattaneo that is going to talk of VV formalism around the code.
Okay. So actually this will start with a basic introduction to VV from scratch. And so the plan of the talk is to introduce VV and to explain why and where it is used. Maybe just well, we come to the details, but the idea of VV can be seen as a generalization of BRST, which applies to more general theories than BRST. This is not his strong point because the theories that for which you need VV and that can be treated with BRST are not that many. I mean, if you go to topological theories, there are more, but for physical theories, not that many. But there are other advantages of VV. Well, one, that even if you stay with theory that you formulate using BRST, you are a bit more flexible in the choice of pitch fixing. But another advantage, which is more important, is its compatibility with partial integration. So if you integrate just a certain number of degrees of freedom, what you can transfer down is a VV structure in a natural way. So this makes VV compatible, for example, with some approach to normalization, but also with the effective action if you integrate out all fits. And another reason why VV is also turns out to be important when you start dealing with theories defined manifolds with boundary, and the compatibility between the bulk theory and the boundary theory becomes very natural in the context of VV, even if you start from a theory for which BRST is enough.
You know, I hate to interrupt, but theories on a manifold with boundary is too vague a concept because it means two completely different things.
Yeah,
local boundary conditions, like for the air at the end of this room.
Yes.
And there also are global boundary conditions when you're specifying an initial state.
Yes. Now, so for me, boundary is like just means that the manifold in which you define the theory as a boundary, and then you decide what to do with this boundary. There are these two possibilities.
Okay.
That's
So your statement was meant to apply equally to both possibilities.
Yes. So here is the plan of these two talks. So first of all, I will recall you what is VV locally. That's in local coordinates. It's just some simple exercise to show why VV works. Next, I will move to VV globally, which gives you somehow the geometrical feeling of what VV is. And well, I will do both of these in the finite-dimensional setting, mentioning what has to be changed to adapt it, at least formally, to the infinite-dimensional setting. And then I will move to its application in field theory, where we show that in which sense VV extends BRST. So essentially what we'll see that in BRST, what basically the ingredient you have is a BRST operator, which is a vector field squaring to 0. And so the extension VV that you make this vector field Hamiltonian with respect to some symplectic structure. And also divergence free in some appropriate way. Then I will shortly mention the AKZ method, which is a method that allows you to construct directly VV action for a certain theory. Well, I think probably short here because Pavel already gave some presentation of it at the end of the talk. Then I will probably shortly discuss this VV push forward of fiber integration in the case of Chern-Simons theory, just as an example. And finally, I will move to VV for manifolds with boundary. At the classical level, so VV is something you implement like BRST before starting quantization. And finally, I will tell you something about quantization. Quantization of VV theories with boundary. And again, so here actually I can speak of corners as well in a natural way at the classical level. At the quantum level, well, we still don't know how to deal with corners, or we'll never know, but we will be able to, but at least with boundary. And the boundary can be treated in two possible ways, as was mentioned. Okay. And finally, but okay, I think probably in this 3 hours we'll arrive here, but if there is some time or maybe after the talk, I'm interested, I could explicitly discuss one simple examples where you want to see the feature of this is to be we have theories. We have theories of manifold with boundary, actually abelian, we have theories as a starting point, and then perturbation around abelian B theory, which could be non-abelian B theories, but also several AKZ models, including Chern-Simon theory with special choice of gauge group. Okay, so just let me start from scratch, from point 1, what is BV locally in finite dimension. So this means that you just have even and odd coordinates, which I will denote by Q upper I and P lower I, for I from 1 to n, so that is finite dimensional. And my understanding is that the degree or the Grassmann parity of the variable Pi is opposite to the parity of the coordinate Q upper I. So this sign is -1 to the degree of the Qi variable. So notice that, for example, if I choose the Qi variables to be even and the Pi variables to be odd, then there is no sign. Or maybe there's just some global sign, or sometimes I'll put a minus, some global minus sign here. Now, why do you have to put this sign? Well, this will appear for several reasons. One reason is that, well, the main theorem by BV, you might make some computation and you need this sign for this to give you 0 as you want to be, but there are some geometrical reasons for this, namely that another more intrinsic way to define this delta is the following. So if you have a function f, you can associate with its corresponding Hamiltonian vector field using this symplectic structure. And then by using the canonical Berezinian you have on these are N, you can also compute the divergence of this vector field. And you define this to be the BV operator applied to the function f up to some constant. So usually we define delta f to be 1/2 divergence of the Hamiltonian vector field of f, or maybe minus. Well, I think if I want to agree with this formulation, probably I have to put a minus sign here. And now, from this formulation, this science comes out naturally. Okay, so this is now, this BV operator has certain obvious properties. The first property is that it squares to 0. This is very obvious, essentially because when you iterate this, you get now 4 derivatives, the even derivatives commute and the odd derivative anti-commute. So you get symmetric times symmetric. And this another property is that, well, we should see, well, directly from this definition, is what happens if you apply delta to a product. This is not the derivation because it's second order. So there is some extra term, and you can check that this extra term is just a Poisson bracket with respect to this symplectic structure. So and this is called sometimes the BV bracket. Okay, so these is the first property, so maybe let me introduce as lemma 1. This is just a very simple computation. The second lemma is about the main application of BV. So suppose the following, suppose that we have a function of all variables P and Q, and the second functions only all the variables Q. And so I define the integral of f on something I will denote L psi with the same psi here. Just as the following, you take the function f, you set the Pi equal to the derivative of the function psi, and integrate in the Qi variable. So some of these are even, so this is not the integration, some of these are odd, so this is a Grassmann integration. Now the notation L psi has to do with the symplectic interpretation. So here essentially on R and N we have put a symplectic structure omega, and this L psi is actually Lagrangian. So this is a Lagrangian submanifold of well, R n. This is like in ordinary symplectic geometry. If you have a function and you set the p equal to the derivative of this function, this is a Lagrangian submanifold. Okay, now the main lemma is the following. So lemma 2. If the function f is delta exact, then its integral over L psi is equal to 0 for any choice of psi. So this is essentially the main theorem, and whatever else can be derived from this main theorem. And this is just a very simple computation. So, see here. So the proof uses one simple fact, which is essentially the only computation that one has to do it, is the following. So take some function g, for example, the function g appearing there. And suppose that I want to compute this Laplace, this VV operator, so this is di minus 1 qi, and then I want to sum over I. But what I want to do is, first I take the derivative with respect to the p, then I set the pi equal to the derivative of psi, and then I take the derivative with respect to the q. Now this is not the same as doing first both derivatives and then setting the pi equal to the di psi. Right? The reason is that when you set the p equal to the psi, now the p start to depend on the q's. Right? So there is an additional term here, which is like minus 1 qi di dj psi dj di g, and finally you can set the pi equal to di psi. So there is this additional term. Right? So here I'm summing over j, and if I want to get the VV operator, I have to sum over I here, so here's the sum over I and j here. And now the only exercise you have to do is to check that this expression is actually this expression is 0. When you change I with j, this expression changes sign, thanks to this sign here. So this ends up being 0. So this is just a simple computation. So basically what you do, you just rename the indices first. You call ji and ij. To recover this expression, you have to commute the derivatives. This causes no trouble because one is a derivative with respect to an even variable, the other one is a derivative with respect to you have to compute the derivatives here, so you have to exchange two derivatives here, so you get some sign depending on the degree of qi and qj. Here you get another sign depending on the degree of pi and pj, which are shifted by 1, but you also have these other terms, so if you put all the signs together, at the end you get a minus 1. So this is the main point. So the main point here is the computation is that computing the VV operator first and then restricting to this Lagrangian submanifold is the same as taking first the derivative with respect to p, restricting, and then taking the other derivative. And now assuming, so in this lemma you assume there are no contributions at infinity, so this all your function vanish at infinity, then what you are left to when you do integral of delta g, right, by this formula, this is the same as taking the integral of the sine minus qi dig restricted here, and this is 0 just because you have a total derivative. Okay, so that's the only computation you have to do. Okay, so this is essentially basically the only thing you have to know about VV. But out of this you can get a lot of other information. So, namely, there is another lemma which is more important than this one, but can be derived from this one, which is the following. Suppose that now you have a function f and psi as there, but now you just assume that f is delta closed instead of delta exact. And then the statement is that the integral of f on L psi is independent of psi. And we'll see in a moment that this is mainly the application of BV to the gauge fixing problem of field theories. Now, okay, so how do you prove this? Well, you take a family of psi t. You take a family of function psi depending on some parameter t.
So you mean it's independent of psi within a family, actually?
Within a family, yes, yes. Well, but these are just, in this setting, the psi's are just functions on the cube. So just, I mean, this space is connected. We'll see more generally when you go to more geometrical picture.
Not exactly. Well, yes, only to the extent that you chose the Q's at the beginning. You started in Rn.
Yeah.
So there are different
at this level, I'm not changing this psi to another Lagrangian. I'm just working in the space of this Lagrangian submanifold that projects to the zero section. Yes. So let's take a family psi t. For example, you can also take the original psi multiplied by t, right? And let me define zeta t to be the integral of f on L psi t. So what I want to show is that zeta t dot is 0. So let's compute zeta t dot. Well, by our definition, what is this? This is the same as saying, well, this is the same as integrating f with the p equal to the derivative of psi t and then integrate in the q variables, right? So if I change psi, basically what I do, I change the values of the p. So this expression is, okay, up to sine, you can put the sign correctly. This is, I could take the upper derivative of f times the IC t dot. So this is how this restriction changes. And then I have to restrict this to p equal to the psi t, pq1, pqn. And then the main observation is that this expression is equal to delta psi t dot f, thanks to lemma 1 and this condition. So namely by lemma 1, delta psi t dot f is a sum of three contributions. One contribution you have delta psi t dot times f, and this is 0 because psi t dot depends only on the q variables and not on the p variables. The second contribution is psi dot times delta f, which is 0 by this condition. And the third contribution is the Poisson bracket between them, which is exactly this expression. And you don't have the other term since psi dot does not depend on the p. Okay, so now we use the previous lemma, the integral of a delta exact function is 0. And so this shows that this is 0. So this is essentially the end of the proof. So the previous lemma is somehow functional to this lemma. But this is an important lemma. Okay, so I think this is a point. And well, I will go back to field theories later on, but shortly let me tell you what is the reason of this, or what is the application. So the main application, let me state it first to define a dimensional setting. So suppose that you have a function f, which is delta closed, as is here. And suppose that the integral of f for p equal to 0 is ill-defined. Or more generally, suppose that you want to start with some ill-defined integrals. And the idea that you extend your original function to a function that depends also on the p variables, but with this condition. And now the idea is that you replace this ill-defined integral, which is the integral on f on the zero section, by, so we replace this by the integral of f on some other L psi. And as long as this integral is well defined, it does not depend on the choice of psi, because this is what we showed. So this is the motivation.
But if we were just given f of the q's,
Yes.
and it was the ill-defined integral,
Yes.
we'd be a little bit lost. At
Yes.
least at this
No, you
fraction,
need that
how to include
information.
the p's.
You need that information. You need yes. So actually, what you have, also in field theory, what you naturally have is f satisfy more or less this equation, and your original definition of the functional integral is this one, and then you deform it to another one, and this lemma tells you that it doesn't matter how you deform this original f. So this is the main application. So, but before I go to this field theory application, let me generalize this a little bit. So here I presented VV on linear space, Rn. Now I want to extend it to manifolds, so super manifolds, and see a little bit more about its geometry. So next step is the following. So this is part 2. So this is the global version, and mainly this was clarified by Albert Schwarz in 1993, also based on some result by De Witten from 1989. So the idea is the following. So suppose that you have a pair M omega, which is a not symplectic manifold. So this means that M is a super manifold, and omega is a non-symplectic form, which means that it is a non-degenerate closed two form. Okay, so this one ingredient we use locally. The other ingredient we used locally was this integration, which we needed both for integrating and for defining the divergence operator. So the next piece of information actually you're going to add, let me add some piece raw, well, let me add here. So the idea is the following. So pick a Berezinian raw, and if you have a Berezinian, then you can define a divergence operator. So you can define a delta operator depending on rho for a function. So we define delta rho f as 1/2 divergence with respect to rho of the Hamiltonian vector field of f. So the Berezinian enters in the definition of divergence, like also in the case of either manifold. Now, there is one property that is automatically generalized.
What do you mean by picking a Berezinian row? Picking a section of the Berezinian? What do you mean by
a section of a Berezinian bundle.
Okay.
Yes. Yeah. Okay, so you can define the divergence operator, and then it's an easy exercise to see that again you still have this property that delta rho of f times g is the same as delta rho f times g plus minus f delta rho, f delta rho g, plus minus the Poisson bracket of f and g defined through the symplectic structure here. So actually, one important point is that this term does not depend on rho. Okay, whatever rho you pick, this term does not depend on rho. So essentially the point that essentially rho was somehow the first order part of your operator. Well, if you change rho, you okay, we need just make this computation easy to say. Okay, but we had another condition that we used a lot locally, namely delta rho squared to 0, and now this is not automatic. Okay, so so we say that so one say that if delta rho squared to 0, then one speaks, one say that m omega rho is an SP structure. So this is probably an old terminology. So P stands for Poisson, well, symplectic versus Poisson in the sense of symplectic, and yeah, S is related to integration. So, but just the only important point here is to remember that the condition delta square equal to 0 is not automatic. This is a condition on the section of the Brazilian bundle. And well, we see in a moment that you can always find a row with this property. Okay, but if you change row, in general, you destroy this property. Okay, then assume that this is satisfied. Then there are two important lemmas. So lemma 1 says that integral of an exact function on a Lagrangian submanifold is 0. So here I should take integral with respect to the square root of this row. I will explain in a moment what this means. And lemma 2 is as before, if delta rho f is equal to 0, then integral of f on a Lagrangian submanifold is invariant, or doesn't change. Doesn't change under deformations. Under deformations of L. And well, I should explain which deformations I allow. So let me be a bit short here. So first of all, I have to tell you how to define integration, or why this integration on canonical submanifold is automatic, actually canonical. Actually it's canonical up to sign. If you want to fix the sign, you have to fix an orientation, so you have to assume that everything is orientable. So the main observation is the following. Suppose that L is Lagrangian inside M. Then you have the supermanifold version of Weinstein's tubular neighborhood theorem, namely that you can identify the tubular neighborhood of L with its odd cotangent bundle. So basically, you can take the same proof and check that this goes through to supermanifolds. And now the main observation is that if you take the Berezinian bundle of an odd cotangent bundle, this is the same as the square of the Berezinian bundle of the base manifold. So this Berezinian bundle of pi star m restricted to L is the same as the square of the Berezinian bundle of L. So roughly speaking, the reason that somehow, well, basically, if you make a change of variable from one coordinate patch of L to another, on the fiber you change by the transpose of the inverse of the differential, plus you have some off-diagonal block which doesn't enter the computation of the Berezinian. So, but the Berezinian of this, the differential of this transformation is the square of the Berezinian for the change of variables on the base. So this tells you that if you have a section of the Berezinian bundle of M, you can restrict it here, which then by diffeomorphism, actually symplectomorphism, you can map here. So you have a section of the square of the Berezinian bundle of L, and so once you're in L, you can take the square root up to sign, or if you have to choose an orientation. So this integration of Lagrangian submanifold is now canonically defined. So this is the first observation. The second observation is, roughly speaking, the proof of this theorem. But before, actually, let me show that actually there is something stronger. Namely, so here said that if assuming that delta squared to 0, then the integral of a delta exact function is 0. But actually, you can prove also the other way around. If the integral of every exact function on every Lagrangian submanifold is 0, then necessarily delta squares to 0. And it is the following. So near, so say right here, after you're choosing this tubular neighborhood, write rho as the square of a section of the Berezinian bundle of L. And then you can see that explicitly you can compute delta rho of, say, delta rho of G, and see that this is just the same as delta of G plus phi inverse phi bracket G. So what I'm doing here, I'm going, so I write rho as phi squared. I take a coordinate patch here, so just go back to the coordinate picture we had before. So this is the same delta I defined locally. So the modified delta differs from the original one by this extra piece. And so here you can immediately see that this delta rho squares to 0 if and only if the delta of this function phi is equal to 0. So this is just a simple computation. Very often in quantum field theory, you write this phi as exponential of IH bar s or minus s, depending on this. Then this condition is equivalent to the condition that I think IH bar delta s plus 1/2 s bracket s is equal to 0, and this is the whole quantum master equation. But we will return later to this. So actually this shows already that not every rho is compatible with BD in the sense that delta rho square is not 0, but it also tells you the condition that is local. Okay, now
So, not sure if I understand this. Phi, which is e to the I over h bar s, looks like a function.
yeah, so he actually, sorry. Okay, so actually here, well, let's say dp, okay, dqs and dp's. So I'm going, I take a coordinate patch here, so I may write rho as this Perezzinian times the square of the function.
But there's something you didn't mention.
Yes?
Okay. You started with an ordinary symplectic manifold would actually have a volume form.
Yes,
Now,
but on the non-symplectic manifold you don't have.
Yes, you didn't say that. But
okay. Well, okay. The point is that differential forms are not the same as integral forms of supermanifold. That's the point. So on an ordinary manifold, you have a 2 form. You take its top power, and you get a volume form.
Yeah.
Whereas if this trick doesn't work in the case of supermanifold because
yes, but if you're on a supermanifold with an even symplectic form, even
yes.
though you can't pick a top form, I
Yes.
believe it's still true that an even symplectic form does determine a volume form.
an even symplectic form, does it?
I believe so.
Probably.
We
Yeah.
can
Okay.
discuss
So
it.
think, yeah. Maybe yes. Yeah. Maybe that's yeah.
So, the fact that you can't take a top form doesn't immediately show us, in fact, that it doesn't work for an odd symplectic form.
No. Okay.
But if you take vector space shifted by degree 1 and take, this, delta psi, how can it give a volume form? So if you have only odd guys.
Well, maybe we should discuss later, but I think it does.
Okay, so, but anyway, now the proof for the first lemma is very simple. So in a patch, what you want to integrate is delta rho g times square root of rho. And pay attention to what this is. This turns out to be just delta phi g minus delta phi g. So if you go again, if you go to local coordinates, this times this, okay, times dq1, dqn. So this is another computation you can do locally. Delta of g times the square root of rho. Locally it turns out to be delta of phi g minus delta phi g times this canonical Perezzinian on the base. Now, if you assume delta square to 0, we prove that this is the same as requiring this delta phi to be 0. So this means that locally you are integrating something that is delta exact, and that's what we proved before to be 0. Now, for the next statement, like what happens if you change the Lagrangian. So the observation, simple. So there are 2 changes that you are allowed to do. So the first change is the following. You map, well, the first kind of deformation is Hamiltonian deformations. So this is done as follows. So which means that you start with a Lagrangian L, and you map it to phi t of L, where phi t is a flow, some Hamiltonian flow. which means that we have a function, you compute this Hamiltonian vector field, integrate it, you get the flow, and the statement is that integral over L is the same as the integral over phi TL if you are integrating a delta closed function. Now, for the proof of this, it's good to use the other formula where you define intrinsically the BV operator as the divergence of the Hamiltonian vector field. So the proof is very simple. So take d over dt integral over phi t L of f square root of rho. Now, okay, just make a little bit of computation. What does this mean to change this the manifold which integrate? So this is just the same as integrating over the original L the following expression. Take the Hamiltonian vector field, so say suppose the Hamiltonian vector field on the Hamiltonian function H. So you apply the Hamiltonian vector field of H to F, and well, locally, what you want to integrate is this Hamiltonian vector field times phi plus something like F 1/2 divergence with respect to rho of H, again times phi, and then you have the dq1, dqn. So again, so what I take a two-gonal neighborhood of L, and in the local patch I have this expression. And then the idea is that you show that assuming that delta phi is equal to 0, this is the same as delta H F times phi. Phi times inside. So again, what we are doing here, we are integrating something that is delta exact, and we prove that the result is 0. So this shows that the BV integral is invariant under Hamiltonian flows, but there is actually more, and the more comes from a geometrical interpretation. So this is first of all, there is an interesting theorem by Schwarz, namely that any odd symplectic manifold is canonically symplectomorphic to the odd cotangent bundle of its volume. So actually you have global Darboux coordinates. And essentially one way to prove it is just like basically to use Moser's proof of Darboux coordinates, if in this technique, and to check that this is actually global, because you have no problem in integrating vector fields in the all directions. So essentially, this is a statement. But this is the main point. So you can identify your original odd symplectic manifold with the odd cotangent bundle of its body. This is a symplectomorphism. And once you're here, there is essentially, you can go back to an observation by Witten in 1990, which is the following. So first of all, now you can induce the Berezinian over M by taking a volume form on M. So suppose that V is a volume form on N. Then basically you can define rho, well, you have some reference rho that you can define to be V squared, as V squared, or should write V tends to V to be. So this is a Berezinian section of the Berezinian bundle over here. And then you have also a nice geometric interpretation of the BV operator, namely, you can see that functions over M in this representation is the same as section of the exterior algebra of Tn, which is multi-vector fields. But this turns out to be isomorphic to differential forms on N. And this isomorphism is followed. You start with a multi-vector field, and you map it to its contraction with this chosen volume form. So this maps multi-vector fields to differential forms. Let me call this map tau d. And then it's an easy exercise to check that, or possibly up to sign, delta rho is the same as the RAM operator up to this isomorphism. So composed with tau d inverse. So this in particular shows that delta rho squares to 0. This shows that you have choices of raw for which this happens, namely these choices. And then it gives you also some geometrical interpretation of integration of certain Lagrangian submanifolds. So, next observation is the following. So suppose that C is a submanifold of N. Then you can take its odd conormal bundle. So conormal bundle consists of the covector that vanish when applied to tangent vectors. You change the parity of the fiber so that you can regard it as a submanifold of the odd cotangent bundle of N. And this is out to be Lagrangian. And then the next observation is that if you take a function f and you integrate it over the conormal bundle of C with respect to the square root of this Berzinian, this V, this is the same as integrating the corresponding differential form on the submanifold C. So this puts integration in the BV setting on certain Lagrangian submanifold to just integral of differential forms on submanifolds. And on this side you can use Stokes' theorem. So this tells you that you know that this if, so now you say that you see that delta f is 0 if and only if d tau df is 0. So under the assumption that your function is delta closed, this differential form is closed. And then you can use Stokes' theorem. Basically, you can change this C to a homologous C. And so Stokes' theorem tells you that this integration doesn't change if you replace your C by a homologous one. Now we can interpret it here and say that as long as you take this Berzinian, this integral doesn't change as long as you change your Lagrangian submanifold from one odd conormal bundle to another odd conormal bundle where the bases are homologous. And finally, you can put the two things together. Well, first of all, if your raw, you can actually change this a little bit. Now suppose that your raw is some function phi squared times v squared. Well, basically, what you have to do here is that if you want to integrate f square root of rho, this is the same as integrating f phi square root of v squared. So basically, you're back to this. Instead of integrating f, you can integrate f phi, right? But then you are at the same level. So basically, now this tells you that whenever you're integrating delta closed function with respect to some rho on an odd conormal bundle, this doesn't change if you change the base of the conormal bundle to a homologous one. Plus, you have the other theorem that tells you that you can also change things by Hamiltonian flows. And finally, if you're not satisfied with this, you can also prove that every Lagrangian submanifold of an odd, every Lagrangian submanifold of an odd symplectic manifold up to a Hamiltonian flow is the same as an odd conormal bundle of a submanifold of the body. So you can always use a Hamiltonian flow to deform a generic Lagrangian submanifold to one of this form. So this somehow gives you the general picture. Okay, so this is somehow whatever you should know on BV, and actually this is more or less to the 90s. There is a more recent observation, which is very simple. This is a compatibility between BV and integration. So this is so-called BV push forward. So let me do it here. So BV push forward. And again, I will start again from the local picture. So suppose again that the local coordinates Q1, Qn, P1, Pn. So the idea is very simple. The idea that now we want to integrate only on some of these coordinates. So let's fix some k, right, between 1 and n. And let me split the coordinates. So we have coordinate 1 up to Q, say K minus 1, P1, Pk minus 1. So for these I will use the notation with a prime. And then you have the other coordinate, Qk up to Qn, P lower n up to P lower n, and we use the notation with double prime. So in particular, you can write delta as a sum delta prime by delta double prime, which means you take the same formula before, but here in the sum, I is less than k, whereas here I is greater than equal k. Okay, so this is now, suppose that again, as before, we have a function f that depends on all the p's and all the q's, and the function psi that now depends only on the second set of q variables. Okay? And then what you can do is to do the following. Take the integral of f, set the p double prime variable to be equal to the derivative of this psi, and integrate on the q double prime variables. So this gives you a function of the remaining variables. Okay? So basically what you do, you take the first k minus 1 coordinates, both p and q, as parameters. Consider the remaining space as a symplectic space with a VD operator delta second, and do what we did before, just depending on parameters. So this integration now gives a function of the remaining variables. And the main observation here is the following, that again, if you take a family's psi t, the result is that d over dt of the integral over L psi t of this function f is delta prime exact, assuming that delta f is 0. So, let me be precise. So, you start with the function f of all the variables. You require it to be delta closed with respect to the total BV operator. Integrate only with respect to the last variables, with the gauge fixing with respect to the last variables. And you see that the result, under change of gauge fixing or under change of the Lagrangian, now you get something different. It's not as before, but the difference is something that is delta prime. Okay? And of course, these are all consistent because, like we saw before, the integral of delta exact thing is 0. So actually, what matters in the integration is delta closed function modulo delta exact. So as for the BV integration on the remaining variables, this term is irrelevant. Okay? And the proof is essentially the same proof I did before. Basically, well, I just write down and repeat the same proof and just keep track that integrate only on certain variables. So this is not very difficult, but for some reason was not noticed. If you have this interpretation in terms of integration of differential forms, this is just the fact that if you have a differential form on a product space and integrate on a cycle of one fiber, you get a function on also a differential forms on the other space, and then you have this property, well, essentially use Stokes theorem together with integration or exchanging integration with the differentiation. So you put together Stokes theorem with this other theorem for analysis, and this essentially tells you that, well, essentially this is the same result. If you change, if you move the integration submanifold, integrating the closed form, the result changes by an exact form. Okay, so this is, and once you have this local formula, you can also extend it globally. So globally, you have this notion of BV, fiber integration. So here you can, in here. Okay. So you have this notion of BV fiber integration, namely, you assume that your original odd-symplectic manifold is either a product of odd-symplectic manifold, or more generally, you have a fibration over a lower dimensional odd-symplectic manifold. you assume that this vibration is compatible with the symplectic structure and that your Berezinian is also compatible with this fiber structure. Then if you start with a function that is closed, function on total space that is closed under the total BV operator, integrate it on Lagrangian submanifolds for the fiber, you get some function on the base, which is still delta closed and changes by delta exact term. So actually, yeah, I think, yeah, actually I have two results here, actually I mentioned, forgot one. So if you change this, you get this, and the other result is that, or we should write it here, that if delta F is 0, then delta prime capital F is also 0. So this fiber integration maps delta closed function to delta prime closed function, and if you change the integration, you change the result just by delta prime exact term. Okay, so maybe before I go to field theory, let me make one final remark about the global version. So one annoying thing in what I said so far that you have to choose a Berezinian. As was said, there is no canonical Berezinian compatible with the BV structure, with the symplectic structure. So this shows that there is no canonical delta BV operator. But this is true only as long as you want to work with functions. So there is a nice observation by Voronov and Kudaverdyan that shows that actually you have indeed a canonical BV operator if you work with half densities. So this is Voronov, Kudaverdyan, Voronov, well, very recently 2000 something. So you have the following. So take half densities on M. So half densities are section of the square root of the Berezinian bundle. There is a canonical Berezinian. There is a canonical BV operator. There is a canonical operator delta with the property that delta squares to 0. You can no longer say that this delta is a derivation up to the BV bracket because half densities are not an algebra. If you multiply half densities together, you don't get a half density, you get a density. Okay, so that's the price you pay for moving from functions to half densities. But if you work with half density, you have a canonical BV operator delta that squares to 0. You have a canonical way of integrating half densities on Lagrangian submanifolds, and you can prove the BV theorem for this half density. So if you have the delta closed half densities, its integral is invariant under the formation of the Lagrangian submanifolds. Okay. There is so how do you prove that there is a canonical Berezinian? Well, the original proof by Kudaverdyan and Voronov was to write down an expression and show that it is well defined. There is probably a nicer version due to Chavera, which is the following. So you start with your odd symplectic manifold omega, consider differential forms on omega. So omega is a supermanifold, these are differential forms, not integral forms, just differential forms. But you have a special differential forms omega, so omega is a 2 form, and since it's odd, omega, wedge omega is 0. Okay? This follows from the fact that omega is odd. Now, what you can do is you define an operator delta on differential forms, which is just taking wedge product with omega. And because of this property, delta squared is 0. Okay? So this is a coboundary operator on the space of differential forms. And then what you can do, you can take the cohomology of differential forms on M with respect to this coboundary operator. And basically, well, Chavera's remark is that this is the same as half densities. Well, canonical isomorphic to half densities on M. Now, the reason that you can compute this cohomology very easily is that omega is non-degenerate. So far here to define delta, I just use the fact that omega is odd. Okay? Okay? But now, if you use the fact that omega is non-degenerate, you have very simple homotopes. Just invert omega, take the corresponding. So this is finite dimension, invert omega. So this way you can completely characterize the homology and explicitly show that it is canonically isomorphic to half densities on M. So this is a different way of representing the half densities. What is the advantage of this? Well, the advantage is that you know that omega is also closed. So this means that delta and D form a double complex. You have a double complex on the space of differential forms, where one coboundary operator is the RAM and the other one is delta. And this cohomology is just the E2 term of this double complex. So what you can do is to compute the induced differential over here, right? The RAM induces some, well, differential and some coboundary operator over here, and you call this a canonical BV operator. Actually, you can check that it corresponds to what you want to have. Well, the correspondence is the following, that you have also a non-canonical isomorphism between half densities and functions. Right? You just pick one half density, right? And actually you pick one delta closed half densities, so you identify your half densities with functions, and over functions you see that this canonical DV operator turns out to be a second order operator like the one we discussed before. So this is the way you go back to the usual description in terms of functions on your manifold, but okay, the point that this is non-canonical.
So, you define the cohomology, but how did you define delta acting on the cohomology?
Oh, because you have a double complex, so there is an induced differential on this. You take a cohomology on respect to delta, there is an induced, well, coboundary operator induced from the other coboundary operator. Okay, so this is essentially picture. And
so concretely, it means you have something annihilated by delta and you act on it with D.
Yes.
And then you consider that mod delta.
Yes. Well, if you only do that, you get zero. You have to go one step further. The first induced. Well, basically you have to take the spectral sequence for this double complex. So this is the E2, the spectral sequence. You compute the induced differential, it's 0. So this is also E3, and then you have an induced differential there that turns out to be this delta. Actually, it's a bit more complicated, but essentially this is the idea.
Delta is in E3 then? Or
Yeah.
in E3?
Well, but this E3 is the same as E2 because the second differential is 0.
Ah, okay.
Yes. Okay, and maybe let me just say the last thing about this finite dimensional BV formalism is an application. So integral forms.
So, roughly speaking, it means fun. You act with D,
Yes.
that's a negative of something, and
Yes.
then you act with D on that.
Yes. Okay. Yes. Exactly. You do. Yeah. You
That's
have to
why
do
it's
it
a
twice.
second order.
You have to do it twice. Yes. Exactly. That explains why second order. Okay, so an application of this is actually the notion of integral forms on supermanifolds. This can be introduced in different equivalent ways. There is a nice way to do that, which is by this formalism. So suppose that you start with some supermanifold n, any supermanifold n, and then you define integral forms on n as half densities on pi T star n. You start with your supermanifold n, go to its outcotangent bundle with its canonical out-symplectic form, and you consider half densities on this. And you define this to be the integral forms on your original manifold. So one exercise to check that this is equivalent to the other definitions of integral forms. And the advantage here that now you have this canonical delta. So this is a complex. So this shows that integral forms are a complex, but not an algebra, because you can multiply them, they're half densities. Right? But you have delta, and
Does delta just correspond what I would call D-active integral forms?
Well, if your original supermanifold is a manifold, this
No.
delta.
But even if it isn't, then
Sorry?
even if it isn't a manifold, on integral forms you have an exterior derivative.
Yeah, what? Of course.
You have an exterior derivative.
No, it's something else. It's not, no, it's not the original. I mean, on differential forms on n,
On integral forms, you have an exterior derivative.
on integral form, well, if you define integral form this way, you don't have exterior derivatives.
Well, if you define integral forms as in my lecture, there was an exterior derivative. And now I'm asking whether that exterior derivative maps into delta in the subdescription.
I think, I mean, to do that, you have to, but that's not canonical.
How can it not be canonical? The exterior derivative on integral forms is canonical. So if it does not map into your delta, then it has to map
No.
into something else canonical. I'll ask you what that is.
Now, what you can do, you can identify up densities on pi t star n with functions on pi t star n using, so the non-canonical picture, well, you have to choose a Brazilian on n.
No. Integral forms on n
Yes.
have a canonical exterior derivative. That's completely canonical. So if it's
Even,
true,
even without choosing a Brazilian.
there was no Berzinian in mind. There was
Well,
no.
you have these delta functions, right? That,
What do you think integral forms are?
yes. So he's.
Integral forms are, in my form, well, it's not my formulation in the sense I didn't invent it, but in the
Yeah.
formulation I presented, integral forms are a certain class of functions on pi t star n. On
Yes.
that class of functions, there's a canonical operator, which I call D, the exterior derivative. Now, if integral forms are canonically go over to half densities on pi t star n,
Yes.
D will go to something. I was expecting you to simply say yes when I asked the question. If D doesn't go to delta, what could it go to?
Well, it goes to delta. Well, it depends. I mean, if you stay, okay. Okay, we should go back to see which. Okay, which identification you used to realize integral forms.
I didn't.
Yeah.
I just had a natural definition.
Yes.
There wasn't any.
Ah, no, okay, no, sorry, but it's not an number. Yeah, so it's, okay, what you call D is this then. Yeah, what you call D was not the D, the round D of the differential form. No, okay, yeah, sorry, the answer is yes.
Well, the way I formulated it was you asked on what kind of objects can D act.
Yes,
And one of them was integral forms.
yes,
I see, okay.
but they are not an algebra. Yeah. No,
So
it's the same.
the
It's the
answer
same.
is trivial,
It's the
yes,
same.
by now it's clear. Because D was dq times d by dq.
Yes,
But
it's the same.
some of the dq's are really d by d something else's.
Yes, then I think it's the same. Yeah, you have once, yeah. If you go from the description to the other, your canonical D is the same as this canonical delta. And this is not an algebra, like in your case. But then you can, okay, so this shows that you can, so basically you define integral forms as this complex, and you have Stokes' theorem in the sense that if now C is a submanifold of your supermanifold, and you define the integration of, well, your integral form F over C, this is defined as the integration of F regarded as a half density on the odd conormal bundle of C. So this is very similar to what I said before. The only difference is that what I said before, I assume N to be the body, so it was an ordinary manifold, now extend this to supermanifolds. And basically, the even case has this advantage that basically half densities on pi t star n, when n is just an even manifold, this is canonically isomorphic to differential forms on n. This is because, well, essentially, half densities are roughly speaking the same as functions on pi t star n, tensor top forms on n. You just contract and you get the differential form. So this cannot be repeated, but this is not true for supermanifolds. Okay, so this is more or less whatever I wanted to say. Okay, about the geometry of the V. Now we can move to the application in field theory. Okay, so part 3, so application to field theory. So the idea is the following. Suppose that you have a function f of the form I h bar s on M. And essentially the idea that and some, so M omega rho with delta rho square equal to 0. So from now on I will not write rho. I assume that you have some reference rho for which delta rho square is 0. Then, as I said before, what you can do is you can change rho to f square rho. So this is a new Berezinian. And now you have the delta f square rho square is 0 if and only if delta f is equal to 0, which for s written this way is just the same as 1/2 s bracket s minus I h bar delta s equal to 0. And this is the whole quantum master equation. Now, if I want to say all these rigorous lists, I still have to assume that M is finite dimensional. So here in particular, this tells you that you have to think of this function S to be also function h bar in general, because this equation involves h bar. But, well, usually you assume that this S is actually some power 0, some polynomials in h bar. So you write this S as S0 plus h bar is 1, and so on. And then this quantum master equation implies a set of equations, the first of which is just S0, S0, bracket S0 equal to 0. So this is so-called classical master equation. And then the next equation is something like S0, S1 minus I delta S1 equal to 0, and so on. So this is the setting, and somehow very often you try to go backward. So namely you start with some function S0 satisfying this equation, and you would like to find a function S by adding corrections that satisfy this equation. So you have to solve an equation of this kind, and you basically you see that there are abstractions. So essentially what you see here is that this term is out, well, this tells you that bracket with a 0 is differential. This equation tells you that you want delta S1 to be a coboundary. Right? And this is not guaranteed. You can either see that this is a cocycle, but it's not guaranteed that it is a coboundary. So there are, in principle, there are abstractions in the first homology group of S1, bracket with S0. Okay, now the idea is that what want to extend this to quantum field theory. The main trouble is the choice of the Berezinian. This is the same problem as, well, defining functional integration. So usually as a first approximation, you just forget of delta.
Your equation here should have had delta S0, not delta S1.
Oh, delta S0. Yeah. Yes, sir. Yeah,
What your statement is that you start with the classical action that obeys the classical master equation.
yes.
If it fails to obey the quantum master equation, you might be unable to fix it.
Yes, yes. And there are maybe abstractions. And okay, and the point that when you go to quantum field theory, as a first step, basically you just don't introduce the Berezinian because you don't know how to, that would be like making sense of functional integration, which means that you forget of delta, and first of all you just concentrate on this equation, which is on the other hand very well defined if you, for example, if you work with local functionals. Somehow if you have in mind the idea that this should go on, even if you don't know what this delta is, because you cannot define it, anyway you know that the possible abstractions are in the cohomology of bracket with a 0. This is something well defined. So from this point of view, you know what the potential anomalies are. Then, okay, if you want to go on, basically, what is the idea? Well, the idea is that basically what you want to do, you want to integrate I h bar s on some Lagrangian some manifold if everything were finite dimensional, as we said before, and S satisfied the quantum master equation, then you would know that this integral is independent of the formation of L. So this would be the correct statement. Formally, you would like this to be the case. So basically what you do is, for example, if you work into perturbation theory, you start doing perturbation theory of this, and by some regularization, you can now define the analog of delta on Feynman diagrams and check whether you can iteratively define delta in such a way that the quantum master equation is well defined up to the order in h bar and so on. Okay, so this is essentially the point. And so in this setting, this choice is the same as the choice of gauge fixing, even though it's a bit more general. In a moment, I will go back to the example of BRST to match the notation. Once you move to this setting, it's also quite useful to have the notion of a Gauss number. This allows to keep track of a lot of things. So far here I just said omega was a non-symplectic form. Now if you introduce Gauss number, it's better to say that you want the classical action to have Gauss number 0. You define Q to be the bracket with S0, so this will be a generalization of the BRST operator, and the usual convention in BRST is to assign Gauss number 1 to Q. And if you see that Q and S0 are related by the Poisson bracket from this omega, this forces omega to have Gauss number -1. So this is small. Now, if you go to the Z grading, now the natural assignment is Gauss number -1 for omega.
So until now, we didn't need to have an inter-valued Fermat number.
No, you could, like for example, when you want to define the integral forms, there it makes sense really to take the odd cotangent bundle shifted by -1 instead of the odd cotangent bundle, because this way you introduce also grading for integral forms, which is reasonable. And particularly in the case of an ordinary manifold, this is just the same as the usual grading for differential forms. So there are situations also in finite dimension where it's useful to have this Gauss number. Okay, so now let me go to the example of BRST to show how to match things. So let me do BRST for some gauge theory. So usually you start with some classical action A, depending on some gauge fields or a connection one form, and you assume that this is gauge invariant. At least the gauge invariant under infinitesimal gauge transformation in the case of Chern-Simons theory. Now, usually what you do in Chern-Simons is that, okay, so this is defined, you have some principal bundle over some manifold M on which you define the theory. Okay, so this theory will be the integral over M of something, for example, Chern-Simons form or Yang-Mills. So the first thing you do is to promote the generator of infinitesimal gauge transformation to Gauss. So you introduce a Gauss C, which is just a section of the joint bundle, and that's Gauss number 1. And if you want to, well, first of all, let me tell you what it is in the BB picture, and then let me compare with the BRST picture. So if you are in the BD picture, what to do? Well, you need now a non-symplectic structure, and basically what you do is to take the odd cotangent bundle of the space of gauge fields and of Gauss. So you have to introduce other corresponding momenta. So in this setting, the useful notation is to put a dagger or a plus. So these are the momenta for S. So the idea is that basically the symplectic form is something like delta A dagger plus delta C dagger over M. And well, actually here you have to put some pairing. And if you want to do things canonically, basically you see A or delta A1 is a 1 form, so this has to be a top 4 minus 1. So omega D minus 1. So let's say with a this dimension D. So D minus 1 form, taking value in the conjoint bundle. So that you have so this is just a canonical pairing between adjoint and conjoint bundle. And C dagger is to be paired to zero form, so this is a G form taking value in the conjoint bundle. And then, well, you assign also Gauss number, so this is Gauss number 1, this is Gauss number -1, and this is Gauss number -2. And then, well, the solution of the classical master equation is a function of the classical action plus A dagger paired with the AC plus C dagger paired with C bracket C, or the factor 1/2. Now it's easy to see that this has BB bracket 0 with itself, and then you define Q DRST, or just Q, right, as bracket with S, and in particular you see that Q applied to A is just the AC, because this just means like taking the functional derivative with respect to A dagger, and Q applied to C, which is a functional derivative with respect to C dagger, is, well, the minus sign in the convention, -1/2 C bracket C. So this in particular gives you back the original DRST operator as a special instance. But now this Q is extended essentially by the Cattaneo lift to the other fields as well, to A dagger and C dagger. Okay, so now what does it mean to solve the quantum master equation? Well, if these were well defined, this would just mean that you want the divergence of the Berezovsky operator to be 0. Right? So the meaning of the quantum master equation in this setting is that now you want the Berezovsky operator to preserve the functional measure of whatever it is. So from this point of view, you see that the anomaly is related to the usual anomaly, the non-invariance of the measure. Okay, so and maybe let me tell about the gauge fixing. Now, what you do actually for example, in Young-Mills or generally for gauge theory, is actually to enlarge the space of the fields. So first of all, you add some extra fields.
So the reason you do it, presumably the reason is that these fields aren't enough. You couldn't find the good Lagrangians on the...
You can, in the BB setting, you can, but you cannot find a Lagrangian manifold which is given by the graph of a function. I will come back to that.
Just with only these fields, you could find a reasonable
yes,
Lagrangian.
yes. Yeah, I'll come back to that in a moment. So basically what you do, you add extra fields, essentially you add the so-called anti-Gauss bar and the Lagrange multiplier lambda. So this is a 0 form, and well, my notation, this will probably be a top form. And then introduce the so-called gauge fixing fermion. Psi, that depends on, in principle, depends on all the fields. So in the usual BRST, what you do, you start with A and C, you add C bar and lambda, and you do something. Now I want to show you how this something arises from BD. So what you do, you add these extra fields, C bar and lambda, the corresponding anti-fields to make up the odd symplectic structure. Now, a gauge fixing fermion is just a function of all the fields, but not the anti-fields. And then basically you take the Lagrangian sum manifold at psi, which just says that, okay, you set the anti-fields to be the derivative of psi with respect to the fields. So essentially what I explained on the first lecture locally. Now, and the second thing you do is, however, that you want to extend S in a non-trivial way. So basically you have an extended action, which is this action I wrote there, to which you get this other term, C bar dagger lambda. So notice that lambda has Gauss number 0, C bar has Gauss number -1. So this means that C C bar dagger as again cost number 0, so this is again a term of cost number 0. So you have this term, and so, for example, this means that if you take, so take psi to be, let me see. Yeah, okay. So, for example, so the usual psi, yeah, for example, the usual psi is something like C bar D star A, so you pick a metric and some reference connection, you take this term to the pairing, and sometimes you also add something like lambda star lambda with some coefficient, or maybe some other coefficient. Right? So this is a function of sum of the fields, and if you do this, so basically if you do take this as extended, restricted to this L psi, you get the usual answer. So you get classical action. Here you have A dagger. So A dagger has to be equated to the derivative of this psi, which is essentially this C bar. So this you get C bar, D star, DAC, plus you have C dagger, but C doesn't appear here, so C dagger is set to 0, and finally we have C bar dagger here, and oh sorry, this doesn't, sorry, you have to put C bar, otherwise you get the wrong number. So now, yeah, you put C bar dagger equal to this derivative, so you get the term yeah, lambda D star A plus another term lambda star lambda. So this is the usual gauge fixing of a gauge theory by the RST. Okay, now I want to tell you basically that you don't have to, in principle, don't have to introduce these extra variables, even though this is rather convenient when you want to compute the propagator. So the reasoning is the following. Actually, you can do it in general. So suppose that you have a space F, your original BB manifold, and suppose that you extend it this way. So extending means that you add extra fields like the C bar lambda, and you change the action by a term like this. Okay, so this is extension. Actually, think of this example. So this example, F is the original space of fields, connection, ghosts, corresponding other fields, and then we have some extended space. Now, yeah, so actually, let me just take this to be the C bar dagger space. So the first observation is that actually lambda in here is a bit irrelevant. So whenever you have a gauge fixing that depends on lambda, basically you can deform it into a gauge fixing that does not depend on lambda. So for example, here just get rid of this piece. Basically you just take a family of psi where you just rescale this variable lambda with the parameter t, at t going to 0, you get lambda equal to 0. So you get this gauge fixing without lambda.
Aren't we at some risk? But
yeah, some risk, yeah. Yes.
that we'll get an integral that doesn't make sense. Or
Yeah.
imagine it to be substantial.
Yes. You have to make sense in some way, yes. So this is one way of making sense of it. But now, just to describe geometrically what this means. So suppose now, basically, we do this. So now, what does it mean to have this term? Well, basically, the point that this term, IH bar, C bar, lambda, so I don't want to retain lambda here. So basically, I want to integrate with lambda. So basically, I think of this as a delta function that sets C bar dagger equal to 0. So what is the geometrical setting here? So the geometrical setting here is that I have a function psi on this fx, which is also cotangent bundled, I define a Lagrangian submanifold psi in here, right, by setting the antifields to be equal to the derivative with respect to the fields. So this is Lagrangian. Right? But then I have another submanifold C, right, which is given by C bar dagger equal to 0. So this is also submanifold of that extended. And this submanifold is coisotropic. Coisotropic just means that these constraints Poisson commute with each other. So you can make a reduction. So basically what you do, you take C, right, and you mod out by the Hamiltonian vector fields generated by the constraints. These are just well, vector fields in the C bar directions. So this is essentially canonically symplectomorphic to the original space. So now what you can do is the following. So let me call pi this projection. What you can do, you take pi and apply it to L psi intersection C. So now this is a subset, and under some good condition, even a submanifold of F. And since this original L psi was Lagrangian, this is also Lagrangian. Well, actually, since it's infinite dimensional, this is only isotropic, so you have to check that it's zero Lagrangian. But for example, in this example, it turns out to be Lagrangian. Now, let me describe in this example what is the Lagrangian submanifold we have in here. So, in this example, so say in this example, psi was C bar V star A. So L psi just means that you set C bar dagger to be V star A, and A dagger to be I think V star C bar. So I think it depends how you define this, but it's better to define it as pairs. So A dagger is C bar. So this is the Lagrangian submanifold in the extended space of fields. Now, if we intersect L psi with C, what you have to do is to set C bar dagger to 0, which means V star A equal to 0. So when we project down, we get that A must be the star closed, and that A dagger must lie in the image of the star. So this is just a submanifold of the original space of fields. So this is a space of A, C, A dagger, and C dagger. I define this submanifold, this star A equal to 0, and A dagger in the image of the star. And this is Lagrangian. This is directly Lagrangian in the original space of fields. Of course, if you want to compute the propagator, this might not be a good way. It is a good way, for example, in the case of Chern-Simons theory, because you have a way of understanding what it means to compute a propagator with gauge fixing. But essentially, this tells you that you have a Lagrangian already in a non-extended space of fields. In some sense, roughly speaking, if you don't have cohomology, this subspace, this Lagrangian subspace is just the image of the star. I mean, the condition this star A equal to 0, if you don't have cohomology, is equivalent to the condition that A is in the image of the star. And for C and C dagger, well, this is automatic. So basically, you can think of this. And there is also converse to this theorem, namely, whenever you have a Lagrangian submanifold of your original space of fields, or of your original odd symplectic manifold, as I said, by Hamiltonian transformation, then this can be mapped to a conormal bundle, and a conormal bundle can always be described by this procedure. So extending fields. So this was a theorem in ordinary symplectic geometry by Weinstein, that you have this generalized generating function of Lagrangian submanifolds. That is, you extend your original symplectic manifold by a cotangent bundle of some parameter space. You define a Lagrangian submanifold on this extended space as a graph, and then by this procedure you go back to the Lagrangian submanifold in the original space. In ordinary symplectic geometry, there are topological conditions on which Lagrangian submanifold can be described this way, like the Maslov classes, so I'll enter to this description. But in the odd symplectic case, it's automatic because every Lagrangian submanifold is Newtonian equivalent to a conormal bundle. For conormal bundle, we have this description. Okay, so this probably, yeah, probably should stop here. So maybe tomorrow we'll continue this example about Chern-Simons theory, where there's a advantage that you will see that the degree of the form match in a very nice way. So this will be the first example of AKZ, and then I will move on to the context of theory with boundary.
I have a question.
Yeah.
I wasn't quite following how much of this last discussion applies to, I mean, you were doing a gauge theory here,
Yes.
but if you have a reducible theory or an infinitely reducible theory or an open algebra like in supersymmetry that only closes on shell.
Yeah, that's exactly the case for BV. So
yeah, exactly.
From the point of view, somehow, basically, you have to construct the BV action. So you start from the classical action, the symmetry that goes on in shell, and you use this as a starting data to define the BV action. And I mean, the classical theory is that under certain non-degeneracy condition, you can always find a solution to the classical master equation, even though this can be very cumbersome.
Yeah, but I mean, you're writing down a gauge fix fermion.
Yes.
It's not in general, it might be very difficult to find that.
No, this was just an example.
Yes,
Yeah.
but
Yes.
if we're talking about these reducible theories.
Well, in the general BV setting, basically, what the theory tells you that you just have to find some Lagrangian, some non-singular Lagrangian, some manifold. Yeah, it doesn't have to be. Of course, then you have to understand how to compute the propagator there. And for example, tomorrow we'll see, in some sense, why in Chern-Simons theory, for this Lagrangian submanifold, you get indication of what the propagator should be. So I mean, it turns out to be the same as if you extend by this procedure, but somehow you directly have a notion of a propagator there.
More questions? If there are no more questions, let's take this. 1 minute. Remember that at 4